Hello, today we are continuing in our series on GCSE Physics Revision, looking at turning forces, moments and centre of mass. Let's suppose that we have a nut which is going into the paper. And it's a particularly obstinate nut. It's been in there for some time and we need to unscrew it. The way traditionally we would do that is we would put a spanner around the nut and to unscrew a nut you need to turn it anti-clockwise, so we would have to put a force F on the end of the spanner and there will be a distance D between the application of the force and the turning point, the pivot, sometimes called the fulcrum, the point at which the whole thing is going to swivel, because what's going to happen is that the spanner is going to move round in a circle. It's going to turn as you unscrew the nut. And what we say is that the moment of the force that is applied to that nut, the moment of the force, is a combination of, it's a product of the force times the distance. So it's a product of the force you apply to the end of the spanner multiplied by the distance of the force from the turning point. And just to add one final point, the force and the distance have to be at right angles. It's no use applying a force like this. It doesn't quite work. There still will be a component of that force which is pushing down, but there's also a component of this force which is pushing in, which is doing no good at all. So in order for this formula to apply, the force must be perpendicular to the distance. And then you've got your maximum moment of a force. So let's put some numbers on this. Suppose the distance of the spanner is 0.1 meters. In other words, it's a 10 centimeter spanner. So the distance is 0.1 meters, and let's suppose that the force that we act on is 10 newtons. Then the moment will be equal to the force, which is 10 newtons, times the distance, which is 0.1 meters, and that of course is simply going to be 1. And the units are the units of force times distance. The unit of force is a newton, the unit of distance is a meter, so the units of moments of a force are Newton meters. And it is the moment of the force, the size of the moment of the force, that will determine whether you can undo that nut, which is being particularly obstinate. And you'll notice that the moment of the force will increase. So you'll get a bigger moment if the force itself increases. So if you apply more pressure, that will cause the moment to increase. But it's also true to say that the moment will increase if the distance increases. If D increases, you get a larger moment. So one way, if this is a particularly obstinate nut that you cannot unscrew, then one way to solve it is to make the spanner longer. If you can double the length of the spanner, then the moment will be, even if you use the same force of 10 newtons, because the spanner is now 20 centimeters long, that means D is now 0.2, and that will give you 2 Newton meters. So you can double the moment of the force, double the ability to undo that nut, not by putting more force on, but by making the spanner twice as long. You get twice the effect. I now want to turn our attention to what is called centre of mass. The thing about a centre of mass, let's take a regular shaped object. In this case it's a square. Normally of course it would be 3 dimensions, so it would be a cube. But the point about a centre of mass is, which I think pretty obviously is at the centre, the point about a centre of mass is that from a physics point of view, the centre of mass is the point at which all the mass of the object can be regarded as acting. So you could take a cube, which has a mass m, and you can say that from a physics point of view, all of that mass operates from the centre of mass. So the weight or the force acting caused by that body in a gravitational field is mg, and we can say that the whole of that mass operates from the centre of mass. So if you've got a body which has a finite size like this, and you're saying, well, where exactly does the force of that body apply? The answer is that you can regard the whole mass as being at a point which is called the centre of mass, and consequently the force associated with that in a gravitational field is equal to mg. Well, that's fine if you've got a regular sized object. For example, if you've got a circle or a sphere, once again, the centre of mass will by symmetry be the centre of the circle or the centre of the sphere. But suppose you've got an irregular shaped object, something like this. How are you going to find the centre of mass of that? Well, the method of doing it is very simple. What you do is you pin up the body any way you like. You just stick a pin into the body and hang it on the wall. And what's going to happen, well, I think you can probably see what's going to happen. This is going to swivel in this direction, and it's going to kind of oscillate under the pin until it comes to rest. And when it comes to rest, it'll probably come to rest. I obviously can't redraw it exactly, but I think you'll agree it'll come to rest something like that. Actually, that's probably not a good idea, but let's suppose it does. What you do is you then draw a vertical line, directly vertical down on the shape as it comes to rest. So it's, in other words, it's not moving anymore now, and you draw a line vertically. Then you take the pin out and you stick it somewhere else. Let's now stick it, say, here. So once again, this is going to swivel until it comes to rest under the pin. And when it comes to rest under the pin, it's probably going to look something like this. There's the pin, and it's now swiveled until it's at rest here. This will already have a line on it. Remember, it's got a line on it. It's that line there, which you drew when the pin was in this position. Now the pin's in this position and it's come to rest, you draw another vertical line. And the centre of mass is where the two lines overlap. That's how you can determine where the centre of mass is on an irregular shape. Now, why did we say that the centre of mass was on those two lines? Well, let's suppose we put the object on a pin. There's the pin, it goes through here. And let's suppose that the centre of mass is here. If the centre of mass is here, it's because we've defined the centre of mass as the point at which all the mass can be regarded as residing, and therefore the force, the gravitational force, also operates through that centre of mass. If that's the case, remember we always have to go at right angles, then there is a distance d here, and that means there is a moment of a force. The moment is equal to the force, which is mg, times the distance. And what does a moment of a force do? It causes the object to turn. This object will swivel. It will swivel in this direction, because there is a moment of a force which will cause it to do so. When will it stop swivelling? The answer is it will stop swivelling when, let's see if I can draw this, here is the object again, here is the pin. It will stop swivelling when the centre of mass is vertically below the pin. Why? Because the moment of the force then is still going to be force times distance. The force remains mg, but what is the distance, this equivalent distance? Now, the answer is 0. There is no distance. So the moment of the force when the centre of mass is vertically below the pin is 0. There is now no turning force. That's why this doesn't swivel anymore. So a body will always come to rest when its centre of mass is somewhere, you don't know where, but somewhere below the pin. And that's why I drew a line vertically down, because I know that the centre of mass has got to be somewhere on that vertical line. It must be directly below the pin, because if it isn't, then there will be a moment of a force, and that will cause the object to swivel. Once the centre of mass is underneath the pin, there is now no distance here. The distance is 0, consequently the moment is 0. All I knew by doing it once is that the centre of mass must lie somewhere on that line. When I did it a second time, I then got another vertical line, and I know that the centre of mass must lie on this line. And if I know the centre of mass lies on this line and the centre of mass lies on that line, the only place that it can be to satisfy both of those lines is where the two lines cross. So now let's consider a seesaw. A seesaw is of course an object which swivels. It has a turning point or a pivot or a fulcrum, and it can obviously swivel up and down. That's how seesaws work. And what we do is we can put a force on this side, let's call that a force F1. We can put a force on this side, F2, and the distance from the force to the pivot point on this side is D1, and on this side the distance between F2 and the pivot point is D2. Now on this side, this force, which you'll notice is acting at a right angles to the distance, will have a moment. So the moment on the left hand side is going to be equal to the force F1 times the distance D1. That will have an effect of turning in this direction. It will cause the seesaw to swivel in this direction. On this side we've got a moment, which we'll call M2, and that's also going to be equal to the force times distance, which is F2 times the distance from the pivot, D2. And that is causing the seesaw to swivel in that way. It will go down like this. In order for the seesaw precisely to balance, the moments of the forces must be equal. Not the forces, but the moments of the forces must be equal. So consequently, M1 must equal M2, which means that F1 D1, which is the moment on this side, must equal F2 D2, which is the moment on this side. And if those two are equal, then the seesaw will balance. Let's give some examples to this. Suppose that force is 300 newtons. So we're going to assume that F1 is 300 newtons, F2 is 600 newtons, and I'm going to have D1 as 1 metre. What does D2 have to be? So remember, F1 was 300 newtons, F2 was 600 newtons, D1 was 1 metre. What is D2? Well, 300 newtons for F1 times 1 metre has got to be equal to 600 newtons, which is F2, times D2, which we don't yet know. So D2 is going to equal to 300 divided by 600, which is 0.5 metres. So what that meant is that if you had a force of 300 newtons 1 metre away from the pivot, you can balance that with a force of 600 newtons only half a metre away. So the larger the force, the smaller the distance it needs to be from the pivot, because you'll notice it's the product of the force and the distance. So if you increase the force, to get the same moment, you can reduce the distance. Or contrariwise, if you increase the distance, you can reduce the force to get the same moment. So this means that a seesaw, it's perfectly possible to have a seesaw where you balance a very heavy person and a very light person. The way to do it is to take the very heavy person and put them quite close to the pivot, and then you can take a very small person and put them a long way away from the pivot, and the seesaw will balance, because although you've got a very large force, you've got a very small distance, Whereas here you've got a very large distance, but a very small force. And the two multiplied together will equal. Here's an example. Let's suppose we take a girder, steel girder, which has a mass, a weight of 1,000 newtons. And we, as it were, suspend it on a point, a pivot. Obviously what it would tend to do is to swivel down in this direction. Now to stop it from doing that, we are going to suspend it by a steel cable. And that cable, of course, will have a tension in it, and tension is the same as force. So the tension is the force. There's a force acting upwards here, holding the girder up. Where does the girder's mass operate? Answer, centre of mass. So we go to the centre and we say we can regard the whole of the mass, the whole of the weight, to operate from that point. So we'll call that 1,000 newtons operating from the centre of mass. It's a 10-metre long girder, which means that if this is the centre of mass operates at a distance 5 metres from the pivot point. So essentially we've got a force acting downwards 5 metres from the pivot point, and we've got a force acting upwards which is 10 metres from the pivot point, because that's the length of the girder. And if that's going to balance, then the moment of the force which is tending to make the whole thing swivel in this direction, because if this force is going to make this swivel in this way, has got to balance the moment of the force that's causing it to turn in that direction, and if the two are equal, then the girder will remain stationary. So what are the moments of the forces? Well, in this case, we've got a force times a distance, which is 1,000 times 5. And in this case, we've got a force which is unknown times 10. And that means that F is going to be 5,000, which is 1,000 times 5, divided by 10, which is 500 newtons. In other words, the tension or the force in the steel, in the cable, is going to be equal to 500 newtons, and that is going to hold steady a girder whose total weight is 1,000 newtons. Let's think for a moment about how we might use this principle for our own advantage. We can, for example, create a lever. Now, a lever is just essentially a seesaw, but what we do is we use it to lift a heavy object. Let's suppose we've got a very heavy object of mass m, and we are going to push down on the other side with a force F. The force acting in this direction, of course, is simply mg. That's the weight of the object, or the force acting under gravity. And the distances from the fulcrum are respectively d1 and d2. And we know that in order to balance that seesaw, the moment on this side must equal the moment on this side. The moment on this side is mg times d1, and that will have to equal the force times d2 on this side. Now, you can see that if d2 is very much larger than d1, then a relatively light force will lift a very heavy object. It's exactly the same as when we did the seesaw and we had the very heavy person close to the pivot and the very light person far away from the pivot point. If, for example, mg were 1,000 newtons and we had it 1 metre from the pivot point, and then we applied a force 10 metres from the pivot point. So this is 1 metre, but this is 10 metres. Then you can see that the force will equal 1,000 divided by 10, which is 100 newtons. In other words, we can lift a mass, or rather a weight, of 1,000 newtons simply with a force of 100 newtons, provided we are 10 times further from the pivot point than the weight is. In fact, if we use exactly 100 newtons, all we will do is to precisely balance the weight. But if we use 101 newtons, if we just do a little bit more, then we will push this down and we will lift the weight up. And that gave rise to a very famous saying, "Give me a lever and I will move the world." Because the argument is that even if you put the Earth on one end of a lever, provided that lever was long enough, and it would probably have to be several miles long, provided that lever is long enough, then the mass of the Earth, or rather the weight of the Earth, let's call that W, the weight of the Earth times the distance from the fulcrum, which is d1, has got to equal the force I can apply times the distance from the fulcrum, which is d2. And provided d2 is long enough, I can even lift the Earth. Here's a second way in which we can use this turning forces and moments to our advantage: a wheelbarrow. Here's a wheelbarrow with a load, and that load will be the mass of the load times mg. That's the force that's acting down. That's what's actually in the wheelbarrow. And I have to lift up the wheelbarrow with a force F. The pivot point is obviously the centre of the wheel, because that's where the whole thing is going to swivel. As I lift it up, it swivels around the wheel. And once again, let's say that this is a distance d1, and we'll say that the distance to the force is a distance d2. So this is d1, this is d2. And so once again, the moment of the force acting downwards, causing the thing to swivel down, will be mg times d1, force times distance. The moment of the force that I am applying in the other direction is force times d2. And you can see that because d2 is always by definition greater than d1, because the handles are always further away from the pivot point than the load you're carrying, if d2 is always greater than d1, then the force that I apply can be less than the weight of the load. So if the weight of the load is, say, 100 newtons, and this distance is, let's say, half a metre, and that is going to equal the force that I have to apply times this distance, which let's say is 1 metre, then you've got that 100 times 0.5 is 50, is equal to F times 1, which is F. So the force I have to use are 50 newtons in order to lift a load of 100 newtons, because my force is acting twice as far as the load that is acting down. So that means that if I put something in a wheelbarrow, I don't have to exert the same force as the load, because I am exerting a force further away. So that's a very efficient way of doing it. Unfortunately, Mother Nature hasn't been quite so efficient. Let's just consider our arm. Here's an arm, and here's my hand, and I'm carrying a heavy load of mass m, which obviously will have a force mg. The pivot point is clearly here. That's where my arm, that's my elbow, where my arm will swivel. This will tend to make my arm go down, swiveling in that direction. What holds it up? Well, my muscles. So here are my muscles, and they are exerting a force upwards, and that will tend to make my arm swivel upwards. And so in order for my arm to remain steady, the moment of the force acting downwards has got to be equal to the moment of the force acting up. Well, what is that? This distance here, the length of my arm, is probably about half a metre. The distance of my muscles from the turning point, well, that might not be much more than 0.05 metres, in other words, about 5 centimetres. And so now we've got the situation that the force that I have to exercise to keep my arm up, the moment of the force is F1 times the distance from the muscle to the turning point, which is 0.05 meters, has got to be equal to the weight that I'm trying to carry, which is mg, times its distance, which is 0.5. Now, let's suppose that this mass is 10 newtons, or rather the weight is 10 newtons. Then I've got that the force that my muscles have to exercise times 0.05 has got to equal 10, because it's 10 newtons, times 0.5. And that means that the force is equal to 10 times 0.5 divided by 0.05. And that, you'll find, is 100 newtons. So nature has not been very efficient. In order to lift a weight of 10 newtons, my muscles have to apply a force of 100 newtons because, in this situation, the load is further away from the turning point or the fulcrum or the pivot than the muscle is. Consequently, I need a much greater force because the total moment is force times distance, and it's a very small distance, so I need a very large force to compensate for a load which is acting downwards but over a much greater distance. So in that respect, one would have to say that nature has not been very efficient. Now I want to consider tipping. Let's look head on to a bus. Here is a bus, double-decker bus, coming towards us, tyres, there's the driver, and you're looking at the bus head on, and obviously it's on a level road. Suppose it happens to find a road that is not very level, and the road is like that. The bus is now like this. The question is, how much of an angle does it have to go up, let's call that angle alpha, before the bus tips over? Highly undesirable. You do not want buses tipping over. Now the rule for tipping is simply this, that if you take any object, it could be a bus, but let's just take any object at all, we know that that object will have a centre of mass. And it's the centre of mass that is the point at which the whole mass can be regarded as operating, and therefore the force, which is mass times g, is acting down vertically. Now, provided that mass, that force, is acting within the wheelbase, or within the base of the object, it won't tip. But if the mass is acting, obviously it always acts vertically down, if it is acting outside the wheelbase, then it will tip. Why is that? Because this is the turning point, or the fulcrum, or the pivot. That's the point at which the whole thing is swiveling. And if we've got a centre of mass, which means that there's a weight acting to the left of that pivot point, it means that there's a moment of a force that is swiveling in that direction, and that's going to cause it to tip. Whereas, if the object is at that angle, and here is the centre of mass, you'll see that the centre of mass has a force acting downwards, which is within the wheelbase, or within the base. And here's the tipping point, or sorry, the turning point. And now the moment of the force is to the right of the tipping point, and therefore it's going to cause the thing to swivel in this direction, in other words, to go back upright. So if the centre of mass is outside the base, or rather the vertical line acting down, the force acting down from the centre of mass, if that is outside the base, then you've got a moment that will cause it to tip over. If the centre of mass operates in such a way that the vertical force acting downwards acts within the base, in other words, to the right of the turning point, then you've got a moment that will cause this to tip backwards again. So the answer is quite simple for our bus. We must make sure that the centre of mass never arises such that the forces are to the left of the turning point. They must always be to the right. And one way of doing that is to lower the centre of mass. I mean, for example, if I do this, here's the road, very, very steep road now. There obviously is going to be the turning point because it's on that point that the whole bus is going to swivel. If the centre of mass is here, we've had it because the force acts down to the left of the turning point, and that means that the whole bus is going to swivel in this direction and fall over. But if we can lower the centre of mass to say here, now we're okay because now the weight acts downwards through the base, and that's going to create a moment of a force which turns this way according to that pivot point, and that will mean that the bus will stay upright. How can you make a bus have a centre of mass that is very low? Well, the answer is that you have to put a lot of very heavy stuff, a lot of heavy metal at the base of the bus so that you actually bring the centre of mass lower. Let's just think about a pendulum. A pendulum is a weight or a mass on a piece of string which is suspended at a particular point, and what will happen is that that will oscillate backwards and forwards. That's a pendulum. You take the pendulum, you move it to one side, you let go, and it just oscillates backwards and forwards. And what we do is we say that one complete swing, which is a there and back, a complete swing is to go all the way there and come back to where it started. We say that the time taken for that to happen is called the period, given the letter T. And the period is always equal to 1 divided by the frequency. Let's define these terms. The period T is the time taken for the pendulum to do one complete swing, out and back. The frequency is the number of complete swings that the pendulum does in 1 second. And the two are related by T equals 1 over F. I can also tell you, and at A level you'll understand more why, that if we take the length of the string as being equal to L, then the period is going to be proportional to the length of the string. So in other words, the longer the string is, the longer will be the period. And obviously if T increases with length, then frequency will decrease with length because T is equal to 1 over F. As T increases, F must decrease. So if T goes up with length, as length goes up, so does T. It is also true that if length goes up, frequency goes down. So the frequency is lower as length increases, but the time period increases as length increases. Let's just do some typical exam questions on this whole topic that we've covered in this video. First of all, let's go back to the famous nut that we had at the beginning, and this one is going to be operated by what they call an Allen key. An Allen key has a kind of a square dimension, but it's also L-shaped. And you can put the Allen key in both ways. You can either put this end into the notch here and twiddle this end, turn this end, or you can put this end into the notch and turn this end. And what we want to know is, what's the better thing to do? I can tell you that this end of the Allen key is length 12 centimetres, and this end of the Allen key is 3 centimetres. And I can tell you that if you want to undo that nut, you're going to need a moment of 1.8 Newton meters. That's the total moment that will unscrew that nut. Anything less and it's too hard to budge. So which way are you going to put the Allen screw in? Well, let's suppose you put this end in. That means you're going to turn the short end, which means that if this is the turning point, you're actually going to be applying a force on a handle that is only 3 centimeters long. So we know that you're going to need a moment, I'll make that clear, you need a moment of 1.8 Newton meters to undo it. So that means that the moment is going to be equal to the force times the distance. The moment we know is got to be 1.8, otherwise it's not going to unturn, is going to be equal to F times the distance is 3 centimeters, so that's 0.03 meters. And that means that F is equal to 1.8 divided by 0.03, which equals 60 newtons. So I'm going to need to apply 60 newtons to the short end of the Allen key if I want to undo it. Suppose I do it the other way around. Supposing I stick the short end in the notch and turn the 12 centimeter handle. So now here's my notch, but this time I've got a 12 centimeter handle and I'm going to apply a force to it to undo the nut. Once again, the moment is equal to force times distance. The moment is still the same. I still need 1.8 Newton meters to undo the nut. That's going to be the force times the distance, but now that is 0.12 because it's a 12 centimeter length, and that means that force is equal to 1.8 divided by 0.12, and that is 15 newtons. So when I use the long end, when I stick the short end in and turn the long end, I only need a force of 15 newtons. When I put the long end in and turn the short end, I need a force of 60 newtons. So it's much better and much easier to put the short end in the notch and turn the long end. Here's another question which I hope now will be very straightforward. Here's the seesaw. I apply a force of 20 newtons at a distance 1 meter from the turning point. And on this side I apply a force of 15 newtons. Where do I have to put that force of 15 newtons in order that the seesaw will balance? Well, we know that the moments must be equal. The moment on this side is, moment of course is always force times distance. So the moment on this side is going to be the force, which is 20, times the distance, which is 1 meter. And that has got to equal the moment on this side, which is a force of 15 times a distance, which we'll call d. And that means that d is going to be 20 divided by 15, which is 1.33 meters. So I need to put that force, apply that force at a distance of 1.33 meters from the turning point, the pivot, in order for the seesaw to balance. And a final question, which is based on one we did earlier. We're going to have another girder, but this time the girder is going to be balanced near the end, and I'm going to hold it up to stop it from tipping in this direction. I'm going to hold it up with a cable which will have a tension or a force in it. I can tell you that the whole of the girder is 3 meters long, and that this bit that overhangs here is 0.5 meters. The entire mass of the girder, the entire weight of the girder is 50 newtons. And so what I'm asking is, what is the tension or the force in the steel cable? Well, once again, we can say that the entire force can be thought of acting from the centre of mass. The centre of mass will be responsible for the weight acting downwards, and that is going to be at the centre of the 3 meter girder, which means that it's operating at a distance of, wrong way, it's operating at this distance from the pivot point, because the pivot point is here. What is this distance? Well, this whole distance would be 1.5 meters because it's half of 3. But actually the pivot point is 0.5 meters in, so this distance is only 1 meter. I'll say that again. The centre of mass is at the centre of the girder, which means 1.5 meters from each end. But since the pivot point is 0.5 meters from the end, that means that the distance from the pivot point to the centre of mass is only 1 meter. So the force acting down, causing the girder to pivot in that way around this pivot point, is 50 newtons times 1 meter. Whereas the cable which is holding it up is going to be the force multiplied by the distance from the pivot point, and that's going to be 2.5 meters, because the whole girder is 3 meters long, but the pivot point is 0.5 meters from the end. So the distance from the pivot point to the cable is 2.5 meters. And so for equilibrium, the moments on each side must be the same. The moment acting down is force times distance. That's 50 newtons times 1 meter, 50 newtons 1 meter from the pivot point, and that's got to equal the force in the cable acting up times 2.5 meters, which means that the force is going to be equal to 50 divided by 2.5, and that's 20 newtons. So what we're saying is we've got a girder of 50 newtons, but in this arrangement the tension, or the force in the cable, will only be 20 newtons in order to stop it from spinning or from tipping in this direction.